Welcome back, and in this lesson we're going to be going over the basics of algorithm design and what we need to understand before we start building an algorithm. Now, algorithmic design is actually pretty simple. It's just a series of simple steps. But these steps are extremely important to follow. These aren't just for our own good, but they're to make sure our algorithm can be repeated by other people. And it makes sure that when we build our algorithm, we go for the most efficient solution possible and don't waste our time with possibly inefficient ways. Now, the first thing is to understand the problem cleanly and correctly. This seems insignificant and many people will skip over it, but this is the most important step. Without cleanly understanding the problem, you could easily build an algorithm that works perfectly well, but doesn't work for your situation. For example, someone might build a sorting algorithm, but they might find out the sorting algorithm they built only works for numbers, but they have a series of non-numeric pairs that they need to sort. So we need to make sure that we understand our problem before we do anything else. The result we create from solving our problem also should be in a readable format. It does us no good to say that, well, there's an algorithm that creates an array of sorted values, but the array isn't readable by any real programming language. We need to make sure that when we build an algorithm, it's readable by humans so that other people can understand how the algorithm works, and especially if it's something new, that way they can prove it and they can make sure it works for every single possible solution. We then need to understand the constraints of our problem. This means that we must balance the time we spend coding with the time we save. This is really important because many times people start learning about algorithms and then they spend all of their time trying to optimize. But remember, if all you need is a quick little sort or a quick little solution and you only need your program to work for 5 minutes and it's only going to be working with a 10 value set, then there's no point in spending 30 hours trying to optimize your code. If an algorithm takes way too long to make and it only saves a little bit of time, it's probably not worth it. Remember, your time is extremely valuable. Most of the time, the programmer's cost to the company is more expensive than any computer. As a result, we need to make sure that we reduce the time that we spend coding and use that time more efficiently. So if a problem only needs 5 minutes of work, only spend 5 minutes on it. Don't just code for the sake of coding. So we also have to consider that the data set might be in different ways. This means that we have to consider what is the dataset made up of. So is it all numbers? What pitfalls could potentially arise? Is it all distinct pairs? What are the other big problems that could arise? For example, are they in a string? Are they located in a variety of different locations on the memory? We then must consider if we have a dataset like this. For example, let's say our dataset is all numbers. What algorithms already work and already have been established for these solutions? So there's a lot of algorithms that work for sorting a value of numbers. So we need to make sure we look at the algorithms and we say, do these each apply? If so, we can consider them. Otherwise, we might need to eliminate them. So we have to look at the situation and understand, what does the data come to us as? How are we going to be able to incorporate that into our program? We then need to understand the tool we have and then implement it. We can either try and modify a given tool into from our language, or we can make an entirely new version of an already established algorithm. This means that we can either choose to use our language. For example, we could say that Java already has a sorting algorithm built into it. So instead of building our own sorting algorithm, we simply use the one in Java and then save ourselves plenty of time. Or we could say that, well, our situation is a little bit unique, so we need to make our own version of the algorithm. And as a result, that's going to take a little bit more time to code, but now might be more versatile and might work more efficiently for our situation. Now remember, choosing correctly the algorithm that we're going to implement greatly affects how the problem is solved. If we choose a bad algorithm, then it means that we're wasting a lot of our time and we're going to be wasting time once the program starts running. So we have to make sure that when we make our choice of which algorithm to actually apply, we choose correctly. Spend a lot of time on this step because otherwise you're prone to making a poor choice. General code guidelines still apply, so we still need to comment, indent, and make sure our code is readable by other people. We then need to make sure we test if the algorithm actually works. This is actually pretty important because otherwise we don't know, is the algorithm only going to work theoretically, or does it actually work for a real situation that we have to solve? So our big things are we need to make sure we get complete coverage of a data set. This means that if we can, we should test it against the dataset we have. So if you know that you're going to be sorting a value of 20 integers, and you already have those 20 integers in front of you, then you might as well test your sorting algorithm with these values. However, most of the time, we don't really know exactly what these values are, so we need to pick our data sets a little bit better. Many times, we need to make sure we test the boundary conditions, which are the extremes of the validity range. So, for example, if we need to sort a set of integers, and these integers range from 0 to 100, we should test 0 and 100 to make sure it works. We should test the main values, which are in between the boundary conditions, and then we should make sure we check some error cases and some invalid cases. That way we make sure that if the program runs into an invalid situation, for example a negative number, then we terminate in a clean manner and don't give the user some very harsh termination message. Now, when we have our algorithms, we need to make sure we analyze them as well. What makes a good algorithm? First of all, obviously, it has to work for every single input. This is because, again, computers are perfect, so we expect our algorithms to work for every situation. In addition, our algorithm must be consistently correct. While some algorithms have some randomness built in, this randomness really doesn't affect the output. The randomness is inside of the algorithm, not outside of the algorithm. So we need to make sure that when we have these algorithms, they work consistently, and if they are random, it doesn't affect the outputs. Since we need to be able to rely on these outputs and build on them, many times our algorithm that we implement will only be part of a general program. So we need to make sure that our results can be built on by the rest of the program. Now, we also have to make sure that we can randomize correctly. Randomization is one of the most important things when you're dealing with an algorithm, and many algorithms will need to make sure that if you randomize, it can help reduce the time taken on average. That way we can reduce the worst case scenarios, and randomness is the best way to do this. Sometimes randomness can be very difficult to get working correctly because you can just miss a value, and you might not even notice your error for a while. So make sure that when you're dealing with randomness, you pick correctly. Randomness oftentimes works well, but it can be a very complicated idea. Finally, we need to make sure that if we analyze our algorithm, we have a consistent way to analyze. This means that we're usually going to be analyzing by time complexity. Now, time complexity, there's a lot of ways to do time complexity. We could say that, well, I'm going to run 1,000,000 algorithms, and I'm going to run them on my computer, and I'm going to pick the one with the shortest runtime. However, this doesn't really work well, because again, most of the time we don't know how many values are in our input. What are these values going to range from? So we need to make sure that our algorithms work for most situations, and if we only test a certain number of values, we have no guarantee that for a different data set, another algorithm might not be better. So we need to make sure that when we pick our algorithms by time complexity, we pick the right form of time complexity. This means the time growth rate, because running time depends on system usage and the input set. Growth rate does not. Growth rate is like limits in math. It helps us describe the code that will work for many different inputs, and it helps us determine how will the code scale to different types of values. It can lead to abstract notions and mathematical relationships, which can be somewhat confusing to most people, but for the most part, these won't be a problem. Algorithms will be pretty clean to understand as long as you understand the basics of what we're talking about. After that, the math involved is pretty minimal because most of the time, the math isn't just for math, it's to make sure we understand the time complexity and how will our algorithm scale from 10 values to 100 values to 1 billion values. Remember, scaling is the most important thing when we're dealing with an algorithm, because if we have an algorithm that works well for 10 values but it doesn't work well for 100 values, most of the time we can't stop the user from inputting 100 values. So we have to make sure that depending on the situation, our algorithm still works perfectly. Now, with that in mind, we will usually consider the worst case. This is because it gives a bottom line guarantee of the cost, since most of the time the worst case is what we want to avoid, and the worst case will only occur a couple of times. So if we give a bottom line, if we say that the algorithm will never take more than, let's say, 300 minutes, then we know that if we need to run our program, at worst it'll take 5 hours. In any other situation, it'll take less than 5 hours. Many other algorithms will also have a best case. This is similar to the worst case, but isn't really used that often, because again, the best case is nice, but if the best case is 5 minutes and the worst case is 1,000,000 minutes, then we need to make sure that we don't just work with 5 minutes, because otherwise we'll have unrealistic expectations for our program to work. Now, ideally, we want to make sure we have the average running time, but most of the time, the average running time is very difficult to create. This is because the average depends on so many different values. Since the average could be working for the all extreme values or all of the best case values, we need to make sure that when we create an average running time, we pick correctly. This is extremely important since average running time is the best solution, but if most of the time we won't have it. If you have an average running time, use that because that is the most powerful tool you'll get. We also usually want to know the frequency of the best and worst cases, since many times if we have a best case input, but that best case only occurs one time out of a possible million different input possibilities, but the worst case occurs 500,000 times, then we know that the value will probably skew much closer to the worst case, and we should optimize for the worst case. For example, in many sorting algorithms, the best case scenario is when the dataset is already sorted, and the worst case is when the dataset is sorted in reverse order. So we have to consider what is the probability of the array being already sorted when it's given to us, or if the array is sorted in reverse order. As a result, we have to consider the situation when we're analyzing our algorithms, because otherwise we don't really analyze the algorithm, we're simply analyzing a possible situation. We need to make sure our analysis works for a variety of different types of values. So, hopefully you enjoyed this lesson. In today's lesson, we covered how to design an algorithm. We talked about how you have to make sure you understand the problem. Then you need to make sure you pick the right solution for that problem. And then you need to make sure you test everything so that it works correctly. We talked about why we use time complexity and why we use the worst case scenario most of the time, because most of the time we don't have an average case, even though that's better. And we talked about how randomness can be used in algorithms, but it shouldn't affect the output. The output should always be consistent. And we talked about how randomness can be kind of difficult to implement, but it can help to make sure that we don't have as many worst cases occur or as many best cases. We basically force everything towards the mean. Hopefully you enjoyed this lesson, and hopefully you'll join us for our next lesson, where we'll be discussing a little bit more on how to analyze an algorithm and the mathematical notation of algorithm analysis.